So hello everyone, it's 10 a.m. So I'm going to go ahead and start the recording. We left off on chapter 1 homework, so we should get that done finished today. We'll move on to chapter 2. We'll take a small break in between the chapter 1 homework and chapter 2. And then, we'll see if we can get to the chapter 2 homework. It all depends. So why don't we go ahead and get started. So I'm going to begin sharing my screen. If we can go to screen share, screen 2. And just a quick question, you can just answer this in the chat. Is everyone able to join the room before I enter the room, or do you have to wait till I get here to enter the room? I was just curious. That's just out of my own curiosity. Oh, we have to, okay. So I'm gonna try to get that changed then to where you don't have to wait before I get in here. That's just some technicality that I have to change on my end. All right, so I appreciate that. So I left off, we finished question 3. So we finished question 3 yesterday. Does anyone have any questions about the questions that we did yesterday? All right, so let's go ahead and get started with question 4. So they give us a skeleton of acetonitrile. So here's our skeleton. And it looks like we just have to put the bonds in and the lone pairs. So we're going to have a bond here, a bond here. They're all going to be single bonds to the hydrogen. We're going to have a single bond here because there's going to be usually carbon, it usually wants 4 bonds, and that's generally speaking. And then for the nitrogen here, we're going to do this. And you can always, check the formal charge. Nitrogen wants to be 5, 5 minus 5 equals 0. So this all works out. So while you guys put in the bonds, I'm going to load up the next question. So some of these questions are pretty, fairly straightforward, I'll say. And I will be posting this homework. I'll post the PowerPoint slides to Blackboard, so you'll have this available as well. So it says draw the Lewis structure for carbon monoxide. So we have carbon monoxide, and that's the Lewis structure for carbon monoxide. So that was question 5. And if you ever need more time on a question, just let me know in the chat, or you can shout out loud. Either one is okay. Question 6. Draw the Lewis structure for ammonia. We've seen this. I've drawn this a couple times, I think, in this class. But that's the Lewis structure for ammonia. All right, question 7. Let me see where my pen is. Question 7. It says select the atom or ions drawn with valid Lewis dot structures. You're going to pick, the correct ones with that. So you're going to have carbon with 4, and you're going to have oxygen with 6, and these are the only 2 valid ones. So you have 6 electrons here, you have 4 here, and that's the correct number of valence electrons. So that was 7. Question 8. It says the skeleton of the bicarbonate. So they give you the skeleton of the bicarbonate HCO3-. So we'll go over the formal charges. That way you see how this works here. Draw this a little better. So here we're going to have a single bond. They're going to probably have you do this in the program. We have two lone pairs of electrons here. This is going to be negative. And this will be nothing. So how do you get the minus here? Recall that this is HCO3 minus. If you count, oxygen should be 6 minus 7. You count, there'll be 7. You'll get minus 1. Everything else will get 0 because 1 minus 1 equals 0. 6 minus 6 equals 0. 4 minus 4 equals 0. And 6 minus 6 equals 0. So if you add all these formal charges up, that's what you have to do. So you're adding a bunch of zeros, right? 1, 2, 3, 4, 0. So 4 times 0 plus a negative 1 equals a minus 1. That's how you get the formal charge of minus 1. I guess it'd be the overall charge because you add up the formal charges to get the overall charge. All right. So that was question 8. So question 10, it says we have to, I think this is question 9. Okay, we're on question 9. Question 9 says draw 2 Lewis structures for a compound with C4H10. Well, the easiest one will just be the straight chain. And, this is not even the more difficult one, but you're just going to have a branch like this. All right, so that would be isomers, same chemical formula, but different structures. And this one would have the highest boiling point, and that's due to the London dispersion charges. Remember yesterday we talked about the surface area. So that's question 9. Question 10. It says add formal charges, and I'm gonna CH3. This is CH3. This is a CH3. This has an oxygen. So you have to kind of pick what the formal charges would be. Recall we just did this on this problem right here, the bicarbonate. We found that was -1. And this nitrogen right here, nitrogen should be 5 minus 4 equals +1. So that's how you get +1 here. So what is the net charge on the species? Well, +1 plus a -1 equals 0. So this is what you're going to select. So question 11 says add formal charges of CH3. So when you're done with this, you should have a really good understanding of formal charges. So carbon wants to be 4. 4 minus 3, this is +1. Here we have, let me see, 4 minus 1, 2, 3, 4, 5. So this is -1. Let's draw that a little better for you. So that's how you do that. Is there any other parts to this? Okay, so it wants us to add the lone pair to NH3. So we added the lone pair there. And which atoms have a complete octet? You're going to select, there's 3 answers. You're going to select these 2. Because they do have the octet. The carbon in the CH3 with the lone pair, that has an octet, and then the nitrogen in the NH3 with the lone pair, and that has an octet. Okay, someone put something in the chat. Let me see. Let me see. Did you have the same compound? Okay, so we had someone in the chat. They said that they got it all correct now, so that's good. So that was question 10. This is question 11. Let's go on to question 12. It says for each bond, select the arrow that indicates the directional polarity. Recall. Let me draw the first one, and then we'll recall. Electronegativity increases as you go up and to the right. So where are you going to put this? You're going to have it go like this, right? Then this one will be this way. That way. You're going to have 2 on this one. This one's going to go that way. And then you have the CH3, and this is going to go this way. So that should get you those answers for 12. If you don't understand something, just please speak up too. Question 13 is the same thing pretty much. It just has some slightly different, atoms involved. We're going to draw the line this way for draw the line that way. This even looks like the same answer. Yeah, this is the same thing as last time. So I don't know why they did that to us, but anyways, there you go. All right, so question 14, it wants us to rank the least. I'm just going to put the least here. I'm going to put the most here. So this will be the most positive carbon. And the reason why this will be the most positive carbon is the difference in electronegativity. So that's what we're looking for. That's 14. So let's go to 15. Remember, you come up with this by just looking at the periodic table, looking at electronegativity. You'll find that this is over here, then you have oxygen, nitrogen, then hydrogen, and then lithium. So that's how you rank them. So let's go to question 15. This has to do with, remember, we talked about, let me see, atomic orbitals. So n atomic orbitals equals n molecular orbitals, and the atomic orbitals come in the sides right here. So these would be your atomic orbitals, and then they're going to form some molecular orbitals here. And I might just leave this in here, and one will be bonding, and the other one's going to be non-bonding. So you have bonding. You can have non-bonding or anti-bonding. So it wants us to put in our orbitals. So here we go. And then we're going to have the bonding where they're going to overlap. So this blue one's going to overlap with this blue one. So you'll have this kind of overlap here and down here. So that's why there'll be a bigger sphere, because the overlap. And then if you put one blue one and this one right here, they're going to be anti-bonding. So they're going to kind of pull apart here. And you have that node. So that's that first part. It says select the number of nodes in the atomic orbital. We have 1, as you can see. And the atomic orbital is over here, so that's how you get the 1. It says select the number of nodes in the bonding orbital. So here's the bonding. You have 1 here. And if you look at the anti-bonding, you have 1 right here, and you have 1 right here. That's 1, 2. And then the last part, the last question says, when 2 electrons occupy the bonding molecular orbital in the diagram, what type of bond results and why? And so in the bonding, this is a pi bond. Because the bond is not cylindrically symmetrical about the internuclear axis. So it's not cylindrical. So you're going to look for the word cylindrically. I'm not going to write everything out, but you should be able to find it using these keywords. Does anyone have any questions on that? And like I said, we'll take a break after we do the homework. That'll just give you some time to pull up the chapter 2 homework notes. So, just give everyone some time to think about, and you can go through the chapter 2 a little bit on your own. So we are on to question 16. So when you do these in class with me, this uses your time pretty efficiently, I think. So with this one, we have this right here. This would be positive. So you can see these are 120-degree angles, and apologize for my writing. And then for this one here, these are all the same, so they're all going to be 109.5 degrees. And this is a tetrahedral. This is trigonal planar. In my management class, I'm taking it's organizational leadership, and the big theme in the class is efficiency. It seems like so you always want to make the process more efficient. All right. So we are, what question? That was 16. We're going to go to 17. We have this here. And you should be able to tell why this is positive now. Because 5 minus 4 equals plus 1. So it wants to know the oxygen, this angle right here. And let's find where that angle would be. This is this. We're looking at this right here. I shouldn't draw over it, but they're looking at this angle right there. That's going to be 120 degrees. The next part, they want to know I shouldn't have drawn 4 right there. It's only 3. I was getting ahead of myself. The next one they want to know is this angle right here. And this is going to be 109.5. That was 17. We'll go on to 18 now, or not, yeah, 18. So we have the longest, we have the shortest. So the shortest one will be just a single bond, then you got the double bond, and you got the triple bond. and I'm not gonna, there's 3 hydrogens there. So that's how, because the bonds get shorter as you increase the number of pi bonds. So we went from a single to a double to a triple. Question 19. It looks like I'm going to use a little bit of shorthand here. And we're going to go into the shorthand in the I mean, this is a good segue into the because otherwise I'm going to run, I'm already running out of room here, you can see. So I'm going to have to draw a little my stuff a little shorter. So I got that. I'm not going to draw all the hydrogens because it'd take a lot of time. So what is this bond angle right here? This is going to be 180. Here's going to be another 180. This one will be a 109.5. This one's going to be, let me see. I think I drew this wrong. Sorry about that. It's getting in a rush. I'm gonna have to. So let me see, 109.5. Yeah, this is a 109.5. This one will be a 120. Oh, sorry about that. This is 120. The reason why these are 120s down here, if you see this, if we pull it up like this, and this carbon right here would actually be this right here. So you can see that this would be a 120 now. So I wanted to show that to you a little better. And going up here, we're going to have 109.5, a 120 because we're at a double bond, and another 120. So that should get you where you want to go for this question. Remember, 180 degrees, 180, that's just a straight line. All right. So question 20, let's see what that says. It says complete the table, bond angle in a 2-electron group. Number of electron groups, bond angle. That's going to be your that's going to be 180. That's going to be your typical thing like that. Bond angle in a 3-electron group, 120. Oh, that's really bad. I need to draw this up here like that. The shape of the 2-electron group is linear. It says the shape of electron group molecule with the 2 outer atoms and 1 lone pair. This would be bent. You can think of something like this is bending. Bond angle in a 4-electron group. 4-electron group is usually something like CH4. That should be 109.5. The shape of a 4-electron group molecule with 3 outer electrons and 1 lone pair. You can think of NH3. We got that triangle shape right there, and it's a pyramid. So it's trigonal pyramidal. So why don't we go on to question 21? Question 21. Let me see, what does 21 say? And during the break, I might go ahead and load the PowerPoint, this PowerPoint too for you. So question 21, that way, if you want to go back and check any of your answers, you can do that too during the break. Like I said, I'm going with a more shorthand approach. It just saves me time. This A right here, this is gonna be sp3. That's gonna be 75% P, 25% S. And that's always usually occurs when you have just single bonds. Remember, you have you know, the hydrogens that are the S, you have p orbitals that are involved with the carbon, the py, px, and pz. So carbon A, this is going to be tetrahedral. Carbon, let me just label them, that way I just have a better B, and then this one is C right here. B, this is sp2, you have that double bond. This is going to be trigonal planar. And C right here is going to be just your sp, and that's going to be linear. So that's 21. At 22. We have this right here. And they're talking about this carbon right here. That's an sp3 with 109.5, and it's going to be tetrahedral. Because you have and the reason why that is because you can imagine that these hydrogens are here, this carbon, maybe this carbon's coming out and this one's coming in, so it's going to be tetrahedral. It's going to actually be a little different than 109.5, because if it's truly 109.5, this would all have to be hydrogen. That's going to be slightly different than 109.5, but you'd have no other choice. So, that's the answer that you need to provide. '23 is really easy. It says predict the shape of the water molecule, and that is bent. What number was that? I better write this better, otherwise I'm not going to be able to see what it is. That's 23. 24, I might even write it on the same slide because, they're just asking about formaldehyde. Formaldehyde is a preservative. And this is going to be trigonal planar. It's all on the same plane. So we did 23 and 24. Moving on to 25. It says which molecules have polar bonds? So even though that this is a non-polar substance, carbon tetrachloride, it does have polar bonds, right? Because if we just look at these two atoms right here, these are polar bonds. It is a non-polar substance, but it does have polar bonds. Likewise, you're going to say the same thing right here. This one has it. This one has polar bonds too, because you can have them right here. Even though it's non-polar, carbon dioxide does have polar bonds. Water has polar bonds. I could write that a little better, H2O. And so we have 1, 2, 3, 4 out of them. It says, which are polar molecules now? So now we're going back to the polar molecules. So this is going to be polar. And the reason that's polar is because you have a net dipole here, and then here you have a net dipole here. So this is a polar molecule. All the other ones are non-polar molecules. That's 25. So 26. It says if a solid line represents a covalent bond and a dotted line represents an intermolecular attraction, not inter means between two other molecules. Which of the choices shows a hydrogen bond? Remember, hydrogen bonds are NH, OH, and FH. So, let's see which ones we have, and you should be able to pick that one. So 27. Oh, pen's getting a little on me. Let me erase that. 27 says classify each substance based on the intermolecular, not intra, intermolecular forces. So we have H bonding, dipole. I'm going to use a lot of abbreviations here, and dispersion. So this will be H2O. We have the dipole, and dispersion. This will be HCl and CO. And then dispersion only would be H2. Because there's a dipole with HCl, right? There's a dipole here. There's no dipole here with H. They have one here and they have one here. It's a net cancellation, but there are dispersion forces. So that's 27. We have 3 different molecules. I'm going to use shorthand here. This one only going to have dispersion forces. Here we have another one. This is an aldehyde. Here we have dipole, because there is a dipole here, right? So you have dipole, and you have dispersion forces. And here you have methylpropanol. And this one will have everything. So checkbox for everything. It has hydrogen bonding, has a dipole, it has dispersion. So you have 3 check marks. (29). It wants you to list them from highest boiling point to lowest. Hexane is 1, 2, 3, 4, 5, 6, which have the highest boiling point. It has the highest surface area. So we're looking at surface area. Then we have pentane, 1, 2, 3, 4, 5. So this is pentane, this is hexane, and then neopentane would have the least one because that has, there you go. That's neopentane. It has 1, 2, 3, 4, 5. It has the lowest, this has the least amount of surface area. So if we're looking at surface area, the hexane will have the highest amount of surface area, followed by pentane, followed by the neopentane. So that's 29. And 30. It says, which statement about 2-methyl-1-propanol? And let me just draw that out for you. Let's see. Propyl would be 1, 2, 3. CH2. 2-methyl-1-propanol. Yeah. Draw that out a little better. So it says, which one is more soluble in water? Which statement about 2-methyl-1-propanol and glycerol is true. So let me see something real quick. So this will look like, that's what that looks like, the 2-methylpropanol. And then they want us to look at glycerol. So, and glycerol looks like this. And we have to compare. So look at all the differences is you're going to have more hydrogen bonding with the glycerol than with the 2-methyl-1-propanol. So this is 2-methyl-1-propanol. So you got 1, 2, so 1, 2, 3. That's how you get the, at the 2 position, you have a methyl group, right? I need to write a little better. This is propanol because here you have the propyl group and here you have the alcohol group. So that's how you get the propanol. So the choice you're going to pick is the last one. Glycerol is more soluble in water than 2-methyl-1-propanol because glycerol can form multiple hydrogen bonds, and you can see it can form 3 versus just 1. So that's why you're going to pick the last option. So does anyone have any questions on the homework? So what I'm going to do, we're going to take a break, and during the break, I'm going to stop sharing the screen because I need to put this up. I'm going to keep the annotations. We'll take about a 5-minute break, and then we will come back. If you have any questions, please go ahead, and this should be on the Blackboard site during the break. So I'll see you back in about 5 minutes. Thank you. All right, hello everyone. Hopefully everyone is back and ready to go. We will go into the chapter 2 PowerPoint notes. So during the break, I was able to load up the chapter 1 homework. So everyone has access to the chapter 1 homework PowerPoint notes. Remember, chapter 1 homework is due, and this is for people in the class right now, and this is also for asynchronous crowd students. The homework is due Friday, so please be aware, that you need to follow along in the PowerPoint notes and in the lecture, and you should be able to answer all the questions. So, any questions for me right now? So hopefully everyone had time to take a nice break. I do like breaks myself, and we are now going to go right into chapter 2. So usually, if this was during the regular semester, we wouldn't be going right into another chapter, but we're in a condensed setting. So, we have to do what we have to do. So chapter 2 is molecular representations. And, there are many ways to represent molecules. You could see, I was just in this homework, my pen's not working. Let me get my pen. Oh, I know what I have to do. Sorry about that. I have to enable, it's just a little technical, enable editing for my pen to work. And I'll reshare my screen. And now my pen will work. So you saw in my in the homework session, I wasn't drawing out the whole Lewis structure because that was just going to take me too much time. How I would have ideally drawn a structure like this, I would have just done this right here. I showed the hydrogen right there. It's implied that the hydrogens are here, but it's just an easier way for me to to draw out the structure, and it's to save time. And it's also to save space on paper and digital as well. So consider what information is necessary to accurately describe a molecule. I have everything in here that's necessary to describe that molecule right there. of 2-propanol. So they go into a little bit right there. They talk about isopropanol, also known as 2-propanol. Here's propanol right here. There's no distinction right there because the if you draw it like this, you can put the hydrogen here. If you flip it, the hydrogen will go on the other side. If you just turn the molecule. Here, this is ethyl methyl ether. You have your ether group right here. And the ether group is represented by ROR. And you can see that we have an R group, which is this methyl group, and the other R group is this ethyl group. We saw this example in chapter 1 about the amoxicillin and how much space this would take, as a Lewis structure. And then they show us the bond line structure for amoxicillin. If you match all this stuff up here, they're not drawing this hydrogen right here, and this hydrogen corresponds right here. They're not drawing these pairs of electrons here either, are they? So it's implied that that there's 2 electrons here, there's 2 electrons here. So what I would do is I would study these both structures and see if you can take this structure and make it into this structure, without looking at this, and then check your work. That's what I would do. Again, it's the same thing. So this zigzag, the reason why they have the zigzag, remember there's hydrogens, there's 3 at the end, there's always 2 in the middle. It's because of the bond angles. We talked about, methane. And you can draw it like that, and you can draw it like that. This has 109.5 degrees. Well, that's why we have this zigzag pattern right here. Here we have a linear, and remember there's a carbon here. I'm going to try to draw on the carbons for you. So does anyone have any questions on that? It says linear geometry is drawn for sp hybridized atoms. You can see the linear geometry right here, and this is sp hybridized. So this would be a 180-degree angle. It says carbon atoms are not labeled, but a carbon is assumed to be located at every corner or end point on the zigzag. And you can see that right here. And we're not labeling the carbon atoms on amoxicillin either, but we are labeling we do label sometimes the hydrogens that are important. You can see on this alcohol, on this OH group, that it's important on the NH2, so it's important. Even though that there's a hydrogen right here, no, we don't usually label that. Actually, there is no hydrogen right there. Sorry about that. There's hydrogens here. There is not one right there. There is one right here, though. They're kind of showing you, how to draw, and that, so what you need to do is take a structure like this and then convert it in this and see if you get the same thing. And this is a ketone. Here you have a ketone group, and we're going to go over these groups. A ketone group is represented by this right here, RR. Now, an aldehyde would have been an H with an R. This is an aldehyde. This is a ketone. So you can practice drawing on your own. If you have, this is butane, you should be able to draw 4. It'd just be, I count 1, 2, oh, going a little too quick. Oh, it doesn't want to erase. So you got 1, 2, 3, 4. And it doesn't matter if you would have started up, 1, 2, 3, 4, it's equivalent. Because you could flip it like this, you could turn it over, and you get the same thing as this. So when drawing double bonds, so you don't want to draw the double bonds like this, and that's because of the repulsion right here. These electrons are going to push this bond right here. If you draw it like this, it's more sterically hindered. This doesn't make sense as far as this goes right here. You need to push these right here. When drawing single bonds, the direction in which the bonds are drawn is irrelevant. I mean, this is all the same thing. You know, like I talked about on the amoxicillin, you are going to show that hydrogen with this OH group. Otherwise, if you don't show that hydrogen, this is what this could look like. Let me draw it right down here. Now you may assume that this, you know, is going to have a negative charge right here. So with that hydrogen, you know, we get rid of the negative charge. If you don't have the hydrogen, now this could go on to go on for reactions. And this is the cardinal rule. It says, so they actually should just say generally. And it probably in this class, you're not going to draw, you know, more than 4 bonds to carbon. I know you won't. But other instances, it does happen. Here they're going into some simple organic chemistry reactions, or just, I should just say reactions. They're taking platinum and they're reacting with hydrogen gas, and they're converting this double bond into a single bond. So this will be added like this, and it gets rid of that double bond right there that you can see here. So when certain atoms are bonded together in a specific arrangement, they undergo specific chemical reactions. And it says the characteristics group of atoms are called functional groups. And the functional groups, you know, kind of talked about, it would be, you know, your ketone group, you have an aldehyde group, you know, H, we had that, you know, the ether, and they have a really good table right here. So, you know, here's an alkene. This has a double bond. An alkyne has a triple bond. An alcohol has the OH. The ether is the ROR. The ketone has the 2 R's here. And you can see that the R can be anything, right? It can be 1, it can be 2, it could be whatever it is. Here it's a 2 and a 1, two carbons, and here's 1 carbon on the other side. But if I would have drawn it like H, now it's an aldehyde. And that's how you get the difference between an aldehyde and a ketone. Our carboxylic acid group here, it's an acid group because it can donate that proton right there. An acyl halide is this right here. And an anhydride looks like this. And they have similar chemistry as far as the reactions go. That's why they group them in functional groups. You have a thiol, a sulfide, aromatic. There would be hydrogens all right here, but this is aromatic. Ester, where the R double bonded to the, so this difference between a, this would be a carboxylic acid. Now, if we get rid of the H and switch it out with an R, we have an ester. Amide is here, and an amine is on this one. So the only way to get better at this is just to practice. Let me see. So a carbon atom will have 4 bonds. When it does not, it'll have a formal charge. And you can see why does it have a formal charge here? It's missing a hydrogen, or it's missing a carbon. You know, so we have 4 minus 3 equals plus 1. Likewise here, 1 hydrogen atom on this one. So what I don't like, they should actually draw the hydrogen right there to show that it's to show you that it's missing. So you take 4 minus 3 equals plus 1. Here they said this has 2 hydrogens. It's missing something here. So I'll just say missing. So you take the 4 minus 3 equals plus 1. A carbanion, what's special about carbanions, you know, they're going to be able to attack. You know, they're going to grab something. If you have a hydrogen out there, they're going to be able to grab it. But you take 4 minus 5 equals minus 1. And that's how you get the minus 1 here. Does anyone have any questions so far? All right. So carbon atoms with formal charges. So practice. Try to identify, the formal charges here. Well, let's go ahead and do a couple. Oxygen should be 6. The 6 minus X, and what is our X here? 1, 2, 3, 4, 5. So this would be a +1. This sulfur right here, again, this is going to be 6 minus X, and what is our X? 1, 2, 3, 4, 5, 6. This would be 6 minus 6 equals 0. And you can practice, on your own tonight or tomorrow. Anyone have any questions on formal charges? All right. So they go into some bond line structures, identify lone pairs. Oftentimes you're not, if they show this negative right here, it's implied that that there's going to be these electrons right there. So you take 6 minus 7 equals -1. It says when oxygen has 7 valence electrons, you're going to get a negative. When it has the 6, so 6 minus 6, you're going to have no charge. When you have 6 minus 5, you're going to have a +1. So that's what's going on in this slide. So they talk about oxygen on this slide. Here they talk about nitrogen. Remember, nitrogen wants to have 5 valence electrons, so 6 minus 5 equals, no, sorry about that. 5 minus 6 equals -1. 5 minus 5 equals 0. And 5 minus 4 equals +1. Here they go into dashed lines and solid wedges. So the solid wedges means it's coming out of the display. So you can think of that coming out of the screen towards you. The dashed ones means it's going to be going in. So that's going to be going into your computer screen. So here, this is going to be going in. This one's coming out. This is out. This is in. And likewise right here, this is going to be coming out of the computer screen right here. This one right here. That's just to show it coming in or out of the paper. So Hothworth projections are used only for cyclic compounds right here. Fisher projections are used for acyclic compounds, meaning there's no cyclic structure. Pi bonds or formal charge are often more spread out than a bond line. Structure can apply. So this can jump over here like this. And now the positive charge is over here. So if there's a positive charge here, that implies that there's only one hydrogen. And then you have 4 minus 3 equals +1. And that's how you get the plus right here. So we'll draw that. Now there's a positive charge. Now we shifted it right here because now when you put the bond right here, if that bond's right here, we'll have the there'll be it's now I'll have the 4 minus 4 equals 0. And this is called delocalized. And what that means is it's shared between, and how you depict delocalization, you just draw a dashed line like this. So that means it's delocalized. That means the double bond can either be here or the double bond can be here. So that's what this means right here. And this depiction is a better depiction of what's going on. All right. So if all the carbons have unhybridized p orbitals and all 3 of them overlap side by side, so you can see the overlap right here, and they're all in the same phase. So we would call this bonding. And the next slide shows bonding, non-bonding, and anti-bonding. Anti-bonding means if we draw the carbons like this, and if we draw the p orbitals, one's going to be up, one's going to be down, the other one's going to be up again. And you can see that right here. And the symmetry of the non-bonding, it says the molecular orbital suggests that the cationic charge is spread out to both ends of the 3-carbon chain, not just one carbon drawn with the positive charge. So they're showing you the non-bonding. And what they're not showing you though is, we have n atomic orbitals and we get n, if we have n atomic orbitals, that equals n molecular orbitals. They're showing you the resonance right here, what I showed on the previous slides a couple slides ago, this right here. And they're showing you the 1 resonance hybrid that we talked about. Same thing right here. So you can apply this, not just stuff like this, here'd be your positive and the resonance would say it'd come over here. Now we can start applying it to structure like now. If we draw this, now we're gonna have that bond right here and that positive is gonna shift over here. So you can think, okay, where might, and this happens, where might the positive charge want to be? Will it want to be right here or want to be right here? That's what we're going to talk about later on, in the book. And then depending on where the positive charge is, depends on, where something might come attack it right here, or it will attack it on the end. And you have to think, okay, what is the more stable, and this comes down to stability of the carbocation. So which one's more stable? Well, a secondary carbocation is more stable than a primary carbocation because there's some electrons, sharing, they're contributing to this to this carbocation right here from both carbons, and the hydrogens don't contribute as much. So you can either have electron withdrawing or electron donating. So these carbons are donating some of their electron density to this carbon, so it stabilizes this. So this is going to be probably the more stable carbocation for this instance right here. So they're saying don't break a single bond. You couldn't break single bonds, but it takes energy to do that. And you may ask yourself, well, why is this a bad arrow? Because let's just draw this. It already has an octet as drawn. So if we draw it like this, then we have 5 things around it. 1, 2, 3, 4, 5. So that's why they're saying it's bad. Likewise here, nitrogen is satisfied the way it is because if you take 5 minus 5 equals 0. Now, if you put this right here, let's just do that. Now we have 0, 0, 0, and nitrogen must be 5 minus 1, 2, 3, 4, 5, 6 equals -1. So we put the -1 on the nitrogen, but you always want to put the formal charge on the more electronegative atom, and the more electronegative atom would be oxygen. So that's why you should, learn, something about the trends of electronegativity. So we can have these formations right here, and we put the carbocation right here. The carbon atom does not have an octet, but now you can have reactions happening right here at this point. It says when using curved arrows to derive resonance structure, you'll often have one or more formal charges to contend with. And we saw that. And let's just go on to the next slide here. If we put the electrons right here, we have the double bond here. We put the electrons right here. But we have to show the formal charges to draw it correctly. So here we have, 6 minus 5 equals +1. And here we have 4 minus 5 equals -1. That's how you get the minus right here. So they don't show you that hydrogen right there, but it exists right there. Because if we just look right here, there's a hydrogen right there. So if we shift that right there, so what happens is these electrons, there's 2 electrons here on this double bond, they come right here. When they come right here, you get that negative charge. There are 5 general bonding patterns in which resonance occurs. You have an allylic lone pair, allylic carbocation, a lone pair of electrons adjacent to a carbocation, a pi bond between 2 atoms with different electronegativities, and conjugated pi bonds in a ring. And they go over some examples on the next slides of this. So you have your, this is not allylic, and this one is because it's proximity to this pi bond right here. This is not going to contribute right here like this. But what you could do is put here, and then this could come up here like that. So you can have resonance delocalization. It says all the lone pairs drawn in the examples are allylic. We could put it here, and then this could come here. We could go here, and then this could come here. So you can see how this can work. And they actually show it to you right here. So they're showing you the resonance between the 2 structures. So if they come here, no. Actually, I shouldn't do it like that. They're not showing it exactly like that. So if this comes here like this, for example, this one right here, you have this double bond here, and now you're just going to have that one lone pair, and that other lone pair is going to come up for this nitrogen. Again, they're just showing you delocalization of bonds right here. They do a better job showing you because they're using computer program called ChemDraw to do this, and they can, you know, show it to you. So here are allylic carbocations. You can see that the proxy, so only one curved arrow is needed to show resonance. So if there are multiple double bonds, then multiple contributors are possible. They are drawn by moving one electron pair at a time. So, okay, we're going to move this electron pair. Now we have the double bond here. We have the positive. It went from here and it comes onto this one. So this would be 1, 2, 3, 4, 5, 6. So it comes to, it goes from the 1 position to the 3 position. Now we're going to move it down to the 5 position right here. And the reason why you may do this, because this is the primary carbocation versus a secondary carbocation. And, you know, and we talked about that a secondary carbocation has more stability because the electron donating, in this case, now there could be some electron withdrawing in other cases, but in this case that we're looking at, there's carbons here, they're donating their electrons to stabilize that positive charge. They're showing you some patterns that, you know, you may see. If you see this right here, you can add that double bond. That gets rid of both formal charges. So this is actually a better structure because you see 0 formal charges right here. So whenever you draw structures, you want to get the formal charges as close to 0 as possible. So we have a pi bond between atoms of different electronegativity. The pi electrons will be more attracted to the more electronegative atom, causing the pi bond to be unequally shared. They're showing you benzene right here. And they're just showing you the delocalization of the pi bonds with benzene. If this comes right here, you're gonna, I'm just gonna label these positions. I know they're all equal, but I'm gonna label them so you can see. Now the double bond shifts from the 0,1 position, the 0,6 position to the 1,2 position. Here's a summary of the patterns that we looked at. And you can practice this on your own now. So you can start to see, you know, you can start to jump electrons. It says when multiple resonance structures can be drawn, we know a blend of them, and they're called a hybrid structure. And we saw this hybrid structure right here with this benzene. That's oftentimes you'll see, you know, sometimes you'll see them go like this for benzene just to show the delocalization. It says the carbocation doesn't have a full octet, and this is a better structure right here because in this structure, all atoms have an octet, so it is the major resonance contributor. Here, this is missing a bond right here, so it'd be the less significant structure. This one right here is the more significant structure on the left-hand side. And the reason is we have less, I should say we have 0 formal charges. Here we have, you know, these ones both have formal charges, but it'd be better to have the formal charge on the nitrogen than it would be on the carbon. These are equivalence contributors, just like we saw in benzene. And this one has more formal charges. So it'd be 1, 2, 3. This would be -2. And here we have -2. They're all -2, right? But if you can get the formal charges down to less formal charges, then it's a better contributor. So here we have a total of 4 formal charges, 2, 2, and 2. And we prefer just to have 2 formal charges than an overall 4, even though we get the same number of -2 overall. Likewise, this is more significant than this one because we put the charge here in the carbon, so this would be less. It'd be better to have the charge here, the positive charge on the nitrogen in this case. And you can do this on your own. So resonance hybrid represents the pi bond of a Lilly carbocation as being delocalized over all 3 carbon atoms. We can see that resonance structure right here. This is an amide. So the lone pair of the nitrogen is delocalized because it's next to the carbon atom. So you could do this right here. And they show that on the next slide. It says the lone pair does not participate in resonance if it cannot overlap with an adjacent. So this is kind of important right here. You see this lone pair right here? This lone pair represents this one right here. And you see how that lone pair is just out from the structure itself? It's pointing outwards. This lone pair right here is pointing outwards. It's not going to contribute to the actual structure itself. Now, all these have pi bonds like this. And that's why you're seeing, this is what you're seeing right here. Now, this one kind of has this one, I'm going to draw it like that. It's pointing out. It's not contributing to the overall structure. So that's what's going on in this slide. So it's called a localized lone pair. Since it cannot overlap, it's not overlapping. If we have stuff like this, and then we have a lone pair that's sticking out over here, it's not contributing over here. It's not doing that. So don't assume a lone pair is delocalized just because it is next to a pi bond. Here is a delocalized pi bond. This is a localized pi bond because it's sticking out. This one, there's no other thing like this, so it can't go like this. There's no double bond here, so it's just a localized lone pair. Just like here on ammonia, this is a localized lone pair right here. And that's it for this lecture. So, we'll go into the chapter 2 homework. Does anyone have any questions for me? All right, I'm gonna just need a brief minute to get the chapter 2 homework up. So this will be our chapter 2 homework. So while I'm doing this, you can go ahead and load your chapter 2 homework. I'm going to pause the. So we're back. We're ready to start the chapter 2 homework. I'm going to start screen sharing. So chapter 2. It says draw the Lewis structure for butanol. So the thing what you want to look at, so we're on question 1. So for butanol, this is going to be an aldehyde. So what you're going to draw is they want the Lewis structure, so we'll give them that. All these hydrogens. And more correct, this would look like something like this. And this, I don't know if they're going to accept that, but this is what they want. All right, so that's question 1. Question 2. It wants for each condensed structure, draw the complete structural formula, include all hydrogen atoms. So 1, 2, 3, 4. So this would be 2-methyl butane. So we have so that's the answer to question 2. So for question 3, it says draw CH3, CH, CH3, CH2, CO, CHO. So I would come over here. This is going to be an aldehyde. And that's this structure right here. So this is getting you used to drawing structures in organic chemistry. That's what the purpose of these homeworks are for this chapter. That's 3. Question 4. It says draw the complete structure of butane. So the complete structure, they want you to show all the hydrogens. You're going to show the 3 on the ends. Remember, butane is 4 carbons. And then they want you to show the line and bond. So we have that. That'd be the line and bond. So what you want to know is methane has 1, ethane has 2, methyl ethyl propyl, propane has 3, butane we just drawn that has 4, pentane 5, hexane 6, heptane 7, octane 8, nonane 9, and decane 10. And that'll get you to most structures. That's question 4. Question 5. We have this structure right here. Oh. And the question says, how many carbons? It says we have 2,5-dimethyl hexa 1,4-diene. So let's put that out. I want to show you how you get all this. 2,5-di, and this will be the last question we do. Dimethyl hexa 1,4-diene. So let's try to identify all these parts on here. So it says dimethyl hexa. So let's see. 1, 2, 3, 4, 5, 6. Okay, so it starts right here. 1, 2, 3, 4, 5, 6. That's how you get the hexa. So remember, hexane was 6. Well, that's how you get your 6 carbons. At the 2,5 position, di means you have 2 methyls. So di equals 2. So at the 2 position, you have a methyl group. And at the 5 position, let me see. I might have started wrong, actually. Okay, I started numbering this wrong. I apologize for that. Let me restart my numbers. Here's 1, 2, 3, 4, 5, 6. And the reason, I'll tell you the reason why we start here. You always want to start at a position where you have the double bond. You can encounter that at the 1 position. So if you can encounter that at the 1 here, then you want to start there. Here, there's no double bond at the 1 position. So I did make a mistake there. So at the 2 position, you have a methyl group. At the 5 position, you have a methyl group. At the 1 position, a diene. Remember, di equals 2, and ENE equals a double bond. So at the 1 position, we start our double bond, 1, 2, 3, 4, and at the 4 position, we start our double bond. So you have 1, 2, 3, 4, 5, 6. So 2,5-dimethyl hexa 1,4 diene. So that goes over kind of how the naming of that structure comes about. So here you can see you have three hydrogens. There's 0 hydrogens here. There's 2 hydrogens here. There's going to be 2 hydrogens here. There's going to be 1 hydrogen right here. Here there's going to be 0. Here we count 3, and here we count 3. So that goes over the naming of that structure, where the hydrogens are positioned on that structure, and why, you know, the numbers are on that structure where they are in the naming scheme. So that's all I have for today. So if you have any questions, or, you know, I did tell one of the students to stay back to talk to me. They want to talk about some potential research. Please do, and you're free to go. So I'm going to go ahead and stop the recording. So for all the asynchronous learners, have a great day, and all the synchronous learners, have a great day too.